Hey there, Calc 2 folks, back here with another video in my set of videos for you. Like I said, I'm trying to keep these brief. It's a little easier on me to put them together, and I think probably a little easier on you folks to get through them and keep them all organized in all your work. So I hope that is the case. I took a quick little break there. I don't know. I was over checking out the new look to Facebook. That kind of has a new. I like the new look. I don't know. I put mine on dark theme. I don't know what you folks did, if you're on Facebook even at all, but I kind of like it so far. I haven't spent a lot of time over there, and I don't spend a lot of time over there on Facebook, folks, but just checking it out on a quick little break here. Let's see here. Velocity from acceleration and position from velocity, folks. Those are the next couple of topics we want to get into here. Let me pull those notes up and let's get through this here, and we can all move on. It's been a long day for me, and I got a lot more of these to do for you this week and this semester. So let's get started. Keep in mind, back in Calc 1, we were introduced to the idea of instantaneous rate of change, and one of the places we applied that instantaneous rate of change was looking at the instantaneous rate of change in position with respect to a change in time. And what that describes for us, we understand now, as velocity. On top of that, we also understand that when we look at the instantaneous rate of change in velocity with respect to a change in time, that gives us an understanding of acceleration, right? From our understanding of instantaneous rate of change in position with respect to time, or velocity with respect to time, from calculus, right? We know that when we're given some description of position s of t, that instantaneous rate of change in s of t is going to be given by s prime of t, right? Which is going to yield our description of velocity in our case for motion along a line. Furthermore, if we take the instantaneous rate of change in velocity with respect to time, via t, its first derivative, that would be equivalent to s's second derivative, but in the end would yield a functional description with respect to time for our understanding of acceleration. All right? In this understanding from Calc 1, we understand that if s of t is our position along a linear path at time t, its first derivative yields v of t, this description of velocity, and its second derivative, v's first, yields a of t, our description of acceleration at time t, let's say, respectively. Let's make sure we add that in there, right? So we understand v of t is velocity, a of t is acceleration at time t. All right? Now, moving forward in that relationship from position to velocity and velocity to acceleration requires the process of differentiation, finding derivatives, where we understand there is an inverse operation to differentiation known as anti-differentiation or integration. All right? We can find the antiderivatives and apply the antiderivatives to move backwards through this relationship, going from acceleration to velocity and from velocity to position. All right? That is my next quick little note. This understanding does imply that the antiderivative or the integral can be used to develop a description of velocity from acceleration and position from velocity. And these ideas, right, are summarized in the following two theorems. Let me bring those theorems up into view. Now, I do differ a little bit from the book on these, folks. The book looks at initial values in their calculation. I look at any arbitrary value in my calculation. So that's why these are going to look a little different, but they work very much the same. Here we have our theorem for velocity from acceleration. That's where we would start when working backwards through this process. And it does start off by noting that if we are given some description of acceleration, right, the acceleration of an object moving along a linear path at time t, and given what we note here is our velocity's description at t sub null, or we might just call this t null, right? What t null describes is the velocity of the object at some specific time, t equal to some t null value. T null is going to be some specific moment in time, right? If we know our description of acceleration and we know our description of velocity at a very specific moment in time, then the velocity of the object at times t that are greater than or equal to that very specific moment can be described by the following calculation. All right? They're described by the value here for v of t that is given by the calculation on the right-hand side here. It is the value at v at t sub 0, this value that you will be given in these situations, or have to understand that you know in the start of the problem here. It's a bit that you'd have to also do these calculations, plus this integral. All right, this antiderivative, or this definite integral calculation. This definite integral that starts at a lower bound of t null, that t null being that very specific moment in time being the lower bound, and continuing up through t. Now t, we have to highlight or take note, t is the independent variable of the function. T is going to be variable in this calculation. Nothing goes in for t. T works itself through the calculation as a variable. We're going to apply this integration from the specific value of t to this variable value of t over our acceleration's description, where we've replaced time with just a dummy variable understanding, that being the variable u. Because time, t, is actually going to come back and play a role now as the independent value in our velocities description. And we don't want to leave it in here because our calculation of this would become terribly confusing. So what we do is we just dump out the t. We're going to use that t up here in the upper bound to become this independent variable in our result. And then that t that used to hang out there and be in our description of the parameter for a is just going to get replaced with what we say is sometimes in math a dummy variable. It's just a variable that acts as kind of as a placeholder that works its way out of the calculation in the end. We will see here in just a moment. All right, that's velocity from acceleration. There is another theorem. Looks similar, but that's position from velocity. If you can get velocity from acceleration, and once you obtain a description of v of t, you can take that now and integrate again and come up with a description of position. Right? Given v of t, change around that v, the velocity of an object along a linear path, right, moving along a linear path at time t, and given s of t null, S of t null being the position of the object at a very specific moment in time. At some very specific moment of time, t equal to t null. All right. The position of the object then at times t greater than or equal to t null is going to be described by this calculation given here. That description for s of t, where t is going to play the role of the independent variable, is equal to our very specific observation of position at time t null, added to the the definite integral calculation for our velocity function, where now u again is going to come back and play another role as a dummy variable replacing t, because t again is the independent variable in our result. It's going to play the role of the upper bound in this integration calculation, and t null playing the lower bound. All right. S of t can then be found with this calculation seen here on the right-hand side. Let me illustrate. All right. Here's a classic example. Well, first of all, let's take note of something real quick. Let's take note here. Let's see. What am I doing? Okay. Note, in these descriptions of in these two theorems, I should say, accurate descriptions of velocity and acceleration, velocity from acceleration or position from velocity, you have to have some known information about an observed velocity at a particular time or an observed position at a particular time. All right? The integral calculations we have here, particularly this one here should look familiar. This calculation here we just learned about in the previous video, that's calculation of displacement. We are essentially using displacement in our understanding here to describe the change in position, the overall change in position over some interval of time. But that change in position over some interval of time has to have some time to reference itself from. Or, I should be careful there, some position to reference that change in position from. Some position to reference that displacement from, right? And that is what the observed value of S sub t null is. That is the position from which we're going to then observe a displacement over some interval of time in our description of position. All right? And then similarly in velocity, we have to have an observed value of velocity because all this is giving us is net change in velocity. All right? This is telling us how much velocity is changing overall in terms of a net change, positive or negative in value, right? But we need to have a reference point to reference that from. From what value is it plus or minus from? And that's what V of t null is in the calculation here, folks. All right? So I make quick note of that below, and that is what I'm referencing down there, where now let's jump into a rather classical example. And what a classical example in this case kind of looks like is you are given your acceleration function and you're given a description of velocity and position at at particular units in time. All right. And you might be asked here to determine, let's say here, the velocity function via t and S of t, the position function. Right, let's say that is the direction. That is a rather classical problem. Well, we begin with velocity from acceleration. From our theorem above, velocity from acceleration, right? And from this information, since t null is equal to 0 in value, right? T null is going to be this observed value at time where we observe a very specific velocity or a very specific position. In this case, it's t null is equal to 0. Our description of velocity is just v null plus the integral from 0 to t for our accelerations description, where t, right, has been replaced with the dummy variable of u, and all integrated with respect to u. All I'm doing is going into a at t and replacing that t with the value of u as a dummy variable. T is now going to play the role of a variable on the upper bound of this integration. All right? Implying, if we start to plug and chug on this, v null we know is 4 in value, so we substitute in 4 for v null, or v at 0, I should say, plus the antiderivative of u plus 1 is 1/2 u squared plus u from our fundamental rules. A little power rule and some rule, right? To get us into this antiderivative, where we now evaluate that across these bounds. The lower bound being 0 will give us 0, but an upper bound of variable t just says everywhere you see u, that dummy variable, it gets now replaced with t. That's the statement here. All right? So we're going to have this evaluated at t, that's this, minus this evaluated at 0, which is this. Simplify that. That simplifies into 1/2 t squared plus t plus 4. All right? So I do believe we can then conclude that we now have our velocity function. Our velocity function via t is given by this description, 1/2 t squared plus t plus 4 in value. Now with this velocity description and that little bit of information about known position, right, this information here, I can now calculate my position function. I can now find this value s of t. All right? Let me not go too far here. All right. S at t is just going to be s null, or I should say s at 0, plus that integral from 0 to t, replacing t null with 0 and leaving t as the variable upper bound, and integrating my integrand here, which is nothing more than my velocity function, where this independent variable t has simply been replaced with the variable u. And we integrate that with respect to u. And from our fundamental rules again, right? The 1/2 u squared becomes 1/6 u cubed. U becomes 1/2 u squared, and 4 becomes 4u. So it would be a sum of those four terms. S sub 0, we observed the position at time 0 was 3 meters from the origin. So that is 3, right? And if we now evaluate that antiderivative across these bounds, at t, we just plug in t for all the values of u, kicking out that dummy variable and replacing it with t, right? And then substituting in 0, because of the polynomial form here, that will all zero out. And we'll be left with just the value of 0 there. So simplifying this in a nice descending order, we get the polynomial 1/6 t cubed plus 1/2 t squared plus 4t plus 3. That's our description of position in this case, folks. All right. And I do conclude here. Thus, from the given information about acceleration, along with the specifics about velocity and position, we can just determine these two descriptions of velocity and position with respect to time t. Right? Here's our velocity function. Here's our position function in this scenario, where all we started with in this classical problem was our description of acceleration and a little bit of observed information about velocity and position. All right. And one thing we ought to note is these problems do fit these conditions that are set up by the problem. Via t, it is at the first derivative of this function s of t. And a of t is the first derivative of v of t. Those conditions do hold with these two functions, as well as you'll notice if I plug in 0 here, that will equal 4, and if I plug in 0 here, for all my values of t, that will equal 3 in value. All of the conditions of the problem fit all the initial conditions. All right? So, folks, that is a little bit more into motion in space. I do have a video for distance to give you. I don't know if I'm going to get that done tonight. It's kind of getting late. But you can see these two up by the end of the night tonight. And hopefully you can watch through them before the beginning of class tomorrow, where we are going to perhaps delve into some of these ideas tomorrow. The first chance I get, I'll try to get a distance video up for you, and that will wrap up 6.1 material, and we'll be shortly into 6.2. 6.2 is a short section, folks. So we don't have much to really wrap up this first week, but I do have a little bit of review I'm going to do for you in class, and like I said, we're going to get on that Wolfram Programming Lab, that Mathematica, and do a little work with that and demoing with that, becoming familiar with it early this week. Wednesday is my hopes for that. So, I hope you're all doing well. It's been a long day, I know. I'll see you tomorrow. All right. I'll try to take it easy on you tomorrow. We'll see you then.